So what was the problem again? It was like you have a triangle, right?
And then you have another triangle which sides are.
Oh, the sides are parallel, right?
Yeah, and it's non-congruent.
They're non-congruent.
And prove that. Then you call A and
then if you join these points together,
this is concurrent.
And you join these points together, they're concurrent, yeah? So, I don't know, I did this one a little bit different than just the theorem because it looked interesting another way. I guess if you think about the middle triangle, right?
Yeah.
If you just collapse it to a point, that'd be like the point of concurrency, right?
Yeah.
And it kind of, in 3D, it's kind of like a pyramid, right? A triangular pyramid, where each one of this is like the cross section at every height. You know what I mean?
Also, it always needs some pyramids. Well,
kind of. So it's kind of the way I did it, I think, was, let's see how I did it. I was kind of thinking of it a little bit differently because I was kind of all right with Sever's theorem.
Yeah.
So I got a triangle. And so you can definitely, so like mark in the 2 points, like A and A, B prime, right?
Yeah.
They're parallel, and you can definitely join them, right?
Yeah.
So, let's see, like that, right? And then there's another point. So you can join, like you can make this parallel line, right? So make these parallel lines. And then you can also, I guess, have, what did I do? So I join these first. And then I join this. Okay, and then I guess I made this parallel line intersect here, right?
Yeah.
And then does it suffice to show, this goes there. Does it suffice to show that the line joining these 2 points is parallel to the base?
Yeah. So if you show that, then you show.
Oh yeah. Yeah?
Yeah.
Okay. I just want to do that. Oh, okay. And then to show that this is parallel to the base, right? Well, so you don't really have, you have obviously the common angle, right? You just have to show these 2 triangles are similar, yeah?
Yeah. Yeah.
And you have the common angle, and so you just need to show the ratios are right, yeah?
Oh, yeah.
But then the ratios are right from being these things being parallel, right?
Wait.
So because the ratio of, so x, right?
Yeah.
And big X, yeah?
Yeah.
Is the same as the ratio of like this little z and big Z, right?
Well, no, the angle is just equal. When it never.
Huh? You know what I'm saying?
Yeah.
So the ratio of x to big X is the same as z to big Z, right?
It's the same as that.
It's the same as
it has to be the same as
y to big Y, yeah?
Yeah. So then the whole thing.
So then it's parallel. So then this line must be actually, so then this point must actually be C dash or whatever it is, yeah? Does that make sense?
Yeah.
Yeah, but I think your way is more in line with the theory.
Yes.
You use Sever's, yeah? Okay, and then I'm gonna skip 4. I guess 4 is kind of easy, you just use the cosine rule, but I don't want to labor with the formula. And then I want to talk about the medians thing because that could give us a springboard to today's geometry theory. So the medians thing was, if you draw this line to the midpoint, right? And then draw this line to the midpoint. And the third line, if you draw it, well, one way to say it is if you draw it through that point of intersection, it goes to the midpoint.
Yeah.
Or like if you draw it to the midpoint, it'll go through that point of intersection. Yeah?
Yeah.
And it follows directly from the theorem because this divided by that is 1, that divided by that is 1, right? Yeah, some other ways that are interesting things to think about is like we know that this divides into 2 equal areas, right?
And so it's this one.
Yeah. So if it's 2 equal areas, if you put the line there, it'll balance perfectly on that line, right?
Yeah. That's the weight on either side.
Yeah.
Of the same.
So kind of like the center of mass should be on that line, okay? And by the same reasoning, the center of mass should be on the other line, right? So if you believe the center of mass should exist, then it should be at the intersection of those any two of those lines.
Yeah.
Right? So it's kind of interesting that like if you have a triangle, that point is where you could put your finger on it and it won't fall off.
Yeah.
Right? Okay. Another way to think about it, I guess, that goes into what we're going to do today is, so if we didn't draw this last point here, and we didn't know it was there, right? These are already divided into equal areas.
Yeah.
Okay?
So then,
So if we do join this line up, let's see what I did. Yeah, like if we do join this line up and don't assume it's the midpoint, right? And say this is the area of C and D, right? Can we show that C equals D? Like if C equals D, then this is going to be the midpoint, right?
yeah.
Does that make sense?
Yeah.
So show
It's
C equals D. So I have 2B plus A, right? 2B plus A equals C plus D plus A, because that's a midpoint, so these triangles have equal area.
Yeah.
So therefore 2B equals C plus D.
Yeah. And then
Similarly, from using the other one,
then
2A plus
2A
B
plus B. 2 equals B plus D plus C.
equals C plus D plus B, right?
Yeah.
So then 2A equals C plus D, right?
Yeah.
So actually A and B are the same, right? Yeah. They're both equal to C plus D on 2.
Yeah.
This is all A. And then we know that, remember how we did the ratios? Like the ratio of these 2 areas are equal to the ratio of these 2?
Yeah.
No, shouldn't that mean that?
Yeah.
Yeah. And then 2A plus C. Yeah, I mean the ratio of 2A plus C to 2A plus D is the same as the ratio of C to D, right?
Yeah.
And it's the same as the ratio of 2A to 2A. Yeah? So then we can conclude C equals D. Yeah?
Yeah.
So therefore this has to be the midpoint. Right? So not only is C equal to D, but then actually they're both equal to A, right?
Yeah.
So that was actually one of the theorems. It was like theorem. This is the next we're starting 1.3 now. So 1.3. So we're starting 1.3 now. 1.3 points of interest. POI. Okay. Yeah, so the first theorem was that it divides it into 6 of equal area, right?
Yeah.
So this is 1.31, yeah? Medians of a triangle divided into equal area. Oh, okay. And the second theorem was that is that they trisect each other. Does that make sense?
Yeah.
So this is like 1/3,
And that's
and this is 2/3.
you draw that.
Yeah.
Yeah.
And it's because
You
well,
draw that.
also the areas are 1 to 3, right?
Oh yeah. Because they share.
But which triangle are we looking at though? Let's see. Yeah, I guess if you look at this triangle, right?
Yeah.
Yeah.
Mm.
Then this line divides the areas 1 to 2, right?
1, 2. Yeah.
So then this must also be 1 to 2, the base. Yeah.
Wait, that is.
So this triangle here, like X,
Okay, yeah.
Y, Z, right?
Yeah.
That line divides the area of 1 to 2.
Yeah.
So the base must also be divided 1 to 2.
Yeah.
Yeah. So yeah, so that's theorem 1.2. Medians trisect each other.
It's not 1 to 2. It's 2 to 1 to. Oh no.
Yeah, like 2 to 1. Yeah. Oh, like this is a
Yeah,
third
yeah,
of,
yeah.
and that's 2/3. Yeah. Okay, good.
I think I saw a different original similar trend.
Okay. Yeah, so there's a lot of jargon like circumcircle, circumcenter. We already know that. Yeah. So the intersection of it's called the centroid.
Yeah.
Yeah. That's the center of mass. If you had the altitudes, we talked about the altitudes, right? That's called the orthocenter. Yeah, like if you had the altitude, it's called the orthocenter, right? And it's kind of interesting. Yeah, we'll talk about that a bit later. Okay, and then there's this angle bisector theorem. So 1.33 now.
Like it's listening to the area equal.
Yeah, like it becomes really obvious in this context, right? You have an angle bisector.
The ratio of the areas is the ratio of the sides.
Yeah, so like X and Y, and this is like, this is A,
Should
B.
everyone.
So this is B and this is C, right? So the angle bisector thing is just like X on Y equals, what do you think it is?
The area.
X on Y is equal to C on B.
C on B. So this is like a sine rule thing, right?
Yeah.
Which is even A, right?
It's the
ratio of the areas.
Yep.
So X on sine that, right?
Mm.
Y is equal to C on sine this. And Y on sine that is equal to B on sine that. So X on Y is equal to C on B. Yeah? So the X on sine dot equals C on sine. So this is alpha, I guess. Alpha, and then Y on sine dot equals B on sine alpha, right?
Yeah.
So then that's true. Okay, good. Yeah. Yeah, so I guess they don't really mention it, but you can kind of see if you do that, right?
You can also use it with the areas, right?
Yeah.
Because it's half sine that angle times C, half sine that angle times C.
Yeah.
And the side is shared, so.
Mm-hmm.
And then for the base y and x, then
Yeah.
they share the greater circle. So it's
Yeah.
shared.
So I guess they don't show you explicitly what happens next, but I think it's natural to show you that now the angle bisectors are concurrent, right? See, because so we already know that from doing the incircle, and I guess this is how they can do the incircle. So can you see that for the same reasoning, right? If you do like the angle bisector here and make it like ZW, right? And Z on W is going to equal, you know what I mean? A on C. Yeah. And then if you do another one here, you do another one here,
Yeah.
and it's like U and V, right? Then U on V
It's B.
is B on A, right? So can you see they all cancel when you multiply them together? If you times this by this by this.
You're using the theorem.
Yeah.
Oh, yeah.
So C's cancel, B's cancel, A's cancel, right?
Mm.
So that means they by the theorem, if they multiply to 1, then they meet at the same point, right? But we kind of knew that because that's how you do the in circle, right?
Yeah.
But if you think about it, it's kind of interesting. So if you think about the angle bisector, right? Like geometrically, like every point on this line, right, is equidistant from, like this line is equidistant from those two lines, isn't it? That's the whole point of being angle bisector, right? And so everything here is equidistant from these two lines, yeah? So when they meet, then they're equidistant from all three sides, right?
Yeah.
So that's sort of how the in circle comes about. So that's another way of getting the in circle. Right? And I guess the radius is called the in radius. So theorem 1.34 says that angle bisectors are concurrent. Okay, and we just showed that. And then the concurrency is actually the in center of the, it's called the in center, I guess. Yeah. And the radius of the circle is the in radius. So that's all for 1.3 actually.
Huh?
Yeah.
Oh, okay.
Now we're up to 1.4. It's called in circle and X circle. Yeah, in circle and X circle. I mean, I guess the first theorem, theorem 1.41, right? Yeah. Or maybe this is time to mention that, you know, when you have the altitudes and they come at the point, right?
Yeah.
If you make this triangle here, right?
Yeah.
Can you see that we did that before, right?
Yeah.
Like it also has the lines meeting at the point as well.
Mm.
And the explanation is that they're angle bisectors, right?
Yeah.
So that's explained. I guess you have other situations where. Okay, anyway, so in circle, so the theorem basically talks about when you have a in circle, right?
Yeah. Yeah.
So the tangents are equal. Yeah.
So
This is like so let's draw the same orientation as that. X, Y, Z. This is X, this is Y, and this should be X as well. Yeah. This is X, this is Y, this is Y, this is Z. Yep. This is A, B, C. So this is A, this is B, and this is C. Okay. Okay, so basically, can you see the There's a theorem just basically says what the lengths of these tangents are, like x, y, and z.
Yeah.
So can you see that x is equal to, let's see. So can you express like x, y, and z in terms of a, b, c, and like if s is equal to the semi-perimeter,
Yeah.
can you express x, y, and z in terms of s and a and b and c?
X is equal to s minus a.
S minus a.
Y is equal to. Wait. Plus.
Yeah,
This is what is it? Y is equal to.
Then they all have to be like this
well,
now.
Y is
Right?
equal to s minus b. And
Okay.
yeah.
All right, good. Do we need to prove this?
No.
No, we've done this before.
Yeah.
Okay. So you just have to. That'd be a simple exercise anyway. Okay. Oh, okay. So the next one's pretty interesting, and it's the last thing we're gonna do here.
Oh, so the area formula comes from this.
Oh yeah, did we do the area yet?
The Human's formula thing.
Yeah, I guess you could. So theorem. So this is not the last thing. So theorem 1.42 is that the area is equal to s times the in radius, right?
Yeah.
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 Because
Wait,
the
how do you
area,
get the?
because the area is just half
Now, how do you get
times a plus b plus c, right? so
how do you
that's-
get that square root of the thing? The Human's formula.
Heron's formula.
Yeah, it's like s times s minus a.
The root s times x, y, z.
Oh.
Yeah.
I don't know really how to do it quickly right now.
Does it not come from this? Because like we have
Yeah, I guess like I mean there's a formula for the in radius in terms of the
I think,
sides.
like once you find that, you can just
Yeah.
combine them.
But then I don't know if it's easier or not. Okay, so yeah, so the area thing's done. Yeah, I don't know why these are called theorems. They're kind of maybe they're called theorems for their importance, but not the difficulty.
Yeah.
The usefulness. Okay, so x circles. There's kind of like a nice thing with x circles. So this is 1.43 theorem. So there's a nice diagram here. It's kind of cool. So you draw like a triangle, right? But you extend the sides. Yeah.
Yeah.
And so there's sort of like a circle here called the incircle, right? And then there's like a circle that's tangent to these lines, like that. Yeah. And that's called an X circle. Yeah. Watching. So I guess all four circles are what called like tritangent circles or something. That's what they said. Okay. Okay, so what's the claim? So you see that. Oh, so it's kind of interesting that it's the angle bisector. Well, so I guess now we have to distinguish the internal angle bisector, right? Gets you the center of the incircle. Yeah. Yeah. Like that. Okay. But they interact kind of nicely with the X circle as well. So can you see how like the external angle bisectors meet at the center of the X circle?
Yeah.
Is that obvious?
Yeah, because there's a radius.
Yeah, because like, yeah, you can join the radius and say they're congruent or something. Yeah.
No.
But so this external angle bisector means that, right? And then I guess what the theorem is saying is that they actually meet at the same point as the internal bisectors.
Oh.
So like, if you join, you know what I'm saying? You have like this triangle, like that. And they meet at the center of the X circle.
Yeah.
So I guess one way to argue this maybe is like, well, because the angle bisectors, that line is equidistant from the lines making the angle which is bisecting, right?
Yeah.
So like this angle bisector is equidistant from these two lines, yeah?
Yeah.
And so like the center of the circle is going to be a point that's equidistant from those two lines, right? So it's going to be on that line, you know? And this line is the line that's equidistant from these two lines, right? And so it's going to be on, the circle is going to be on that line as well. Does that make sense? Sorry, the circle here, right,
Yeah.
is the thing that's equidistant from, like the center of this circle is equidistant from these three lines, right?
Yeah.
And the angle bisectors are things which are equidistant from two lines.
Yeah.
The things where they're bisecting. And so this angle bisector is being these two lines, right?
Yeah.
And then this angle bisector is these two lines,
Yeah.
right? So by the time they get to here,
They're equal to all three.
they're equal to all three. And then this bisector, internal bisector, is these two lines, right?
Yeah.
Okay.
Yeah. So like all three are going to be.
Yeah.
Yeah.
And so you get this awesome looking diagram.
Yeah. It looks good.
Where there's like a in triangle with an inscribed circle, right? And then you have these S-scribed circles, yeah, on the outside, which are called X circles, with X centers and X radii. I don't know if this is X radius, maybe that's not a bit too far. Oh, it does say X radii, okay. So there's X radii as well. And then the centers form a kind of a nice triangle, yeah? Yeah. And I guess, you know, they would obviously form a triangle, but the nice thing is that they go through the points of the other triangle. Yeah.
Yeah.
So that's kind of cool. So that's the theorem, but then like also it also mentions some calculations. I would leave these as exercises if we had more time, but basically, because you know what the first theorem was for the length of the in circles tangent things, right? This will be what are the lengths of the tangent things of the X circles, right? So I guess the question is, what is the length of this, right?
Can you just like send triangles there?
There's a lot of them.
Yeah, there's lots of things you could do. So for example, like, can you see these two lengths are the same, right? Yeah?
Yeah.
Yeah, because they're tangents from to the big circle, right? And can you see that if you add them up, right?
Yeah.
What you get is you get these two sides, right?
Yeah.
And then this becomes the same as this,
Oh, yeah.
and this part
you get
becomes the
the
same as
same
this,
Yeah.
right?
Yeah.
So if you add these two lengths up, you get the perimeter of the triangle,
Oh, yeah.
right?
Yeah.
So then each one of these is just the semi-perimeter.
Yeah. My math teacher made us do that as an exercise once.
Oh, really?
And he was like trying to show something, and then I realized it was like that. And then, wow.
Oh, cool.
Yeah.
Yeah, so obviously that's the same for all of them then, right? And then it was saying something
Let's
like,
say
so like the big circles here, the length of these tangents,
yeah.
they're equal to S, the semi-perimeter.
Oh.
And the reason is because, well, if you have 2 times them, right?
Yeah.
Right?
Oh yeah. So that.
Can you see you get the perimeter? Because if you go from here to there, right?
Yeah.
Passes through these 2 sides of the triangle. And then this part is equal to this part.
Oh.
And that part's equal to this part, yeah? Coloring it in has made it whiter. You understand that? Okay, cool. And then there was another thing about what the lengths of what these smaller radii are. A, Y, A. What's that? A, Y, A. It's A, Y, A. No. No, okay. What's BXC? BXC. BXC is S minus A. Okay, so they're saying then this side here, right, is S minus A.
Yeah, we proved that.
Yeah, and I think that they didn't mention that we proved it before, but
Okay, yeah.
I guess. Well, they were saying it maybe for this one, but they're the same, right? So I guess the longer tangents are equal to S, and the shorter ones are equal to S minus A.
And
Yeah.
then that one's
And it's equal to the same as the tangents and the
Yeah.
stuff. Yeah.
And that side should be anyway, so it would be S.
Yeah.
Yeah.
Oh. Okay.
Today in at school we had like assembly we had a concert for the for the shops that they're doing. We had a they had a, like they made a Kahoot to for like alcohol for the entire like school, and then like so there's like 450 people on the
It's like a quiz. It's like a quiz where you enter the code
and
then you join it.
You join the quiz and then you
And it's like a question pattern in the board and you
And
choose
then like
answer.
people, the person who answers the guess them was correct and answers the
And
quiz.
there's like a Hunger Games room as well.
Yeah, and then like
No,
one
there's
of the
rankings.
questions was one of the apparently one of our like prefects had a like has a bodybuilding YouTube channel, and then it like what's the what's his how many views does his most popular video have, and then ranging between like 50 to like a million, and then so we also we didn't think that how popular it was. Turns out the answer was 1.1 million.
Whoa,
Really? Yeah.
Really? People
It was
will
pretty
probably
insane.
get off that.
Whoa.
Wait, so how much money does he get?
It's fair enough. It depends if it was monetized.
Yeah, the business one. So like you could have one popular video.
You could have $1,000 maybe.
That's a
1.1
lot of money.
million. Yeah.
1 million. Some people just post random clips from like movie scenes and they get like 6 million.
Yeah, because for some reason
But you might not get money. Like
Mhm.
it depends on who buys that.
there was this one like because I was looking for this one like significant scene from this movie, and then from like TV show, and then I searched for it. There was only one of them for some reason, and it had like really little views. And someone in the comments is like, "It's the only got that video of this."
Wait, so
It was
what did the comment say?
and then, like this is the only goddamn like of the scene. Have you watched Arrow?
I don't know.
So I watched all the seasons.
I watched like up to like episode 18 of season 7. I should probably finish it.
It's really good. Don't you like watch like one season a day?
That's pretty much what I did, and then
Like I watched the first 2 seasons in a day. It was great.
I got busy for like some time, so I haven't finished it.
Yeah, I guess we're on to the algebra part.
I'm
Like,
supposed to make
I also
algebra.
finished all the seasons.
Huh?
I'm gonna be algebra.
okay. Maybe we're
Like,
gonna.
oh, but yeah, like no one gets.
I guess we're kind of running out of time to go through
That's
too
just
much
one gets
algebra.
erased from the timeline.
But like,
It just ends.
Oh.
Basically, the two things I want to go through.
Basically.
Yeah, okay. We didn't have time to do like some of the stuff I was gonna do, but like, should I leave it for homework?
Yes. Which one?
Is that like too much, too lame?
No, we'll do it. Which one?
Huh?
No, I won't. Still.
Oh yeah. Well, anyway, so like last time we were talking about associativity, like groups, right?
Yeah.
And then I made this kind of wrong claim that like you could do any two pairs, but you can't unless it's commutative, right?
Yeah.
And so like this is not equal to like
A, C,
A C B, right?
Yeah.
Why?
because
And it's not equal to like it's because the
You
point of
can't
the C's
rearrange.
it's C's move past
You
B.
can't
So
rearrange.
that's the problem, right?
Wait, doesn't that dot mean times?
Time.
not
Yeah.
times.
No,
It is
no,
times when it's like
Operator.
yeah, it's an operator.
Some operation.
Yeah. And the problem is, like if you do this, right, you have like BC here and CB here. So if A is the identity 1, right, then BC has to equal CB.
Yeah.
So that doesn't happen all the time. We know there's some groups we have that don't. So if you just produce one of those, it'll violate that. Yep.
Yeah.
Okay. But what I probably wanted to say was that if you had 4 things, right, A, B, C, D, right, you want to write them without brackets. And to be able to do that, it means any way you do bracket them, they'll end up being the same, right?
Yeah.
So it's a consequence of this. So this is the only 2 ways you can bracket 3 things without changing the order, right? But here, there's lots of ways you can bracket things without changing the order. And basically what I'm saying is once this is true, it implies that all those other ways are true equal as well. Yeah? So for example, this, then this, right? Then this, yeah,
That's
is equal to this
Yeah.
and that, right?
Yeah.
So, and all the other ways. Okay, and if you want, you can do it as an exercise. Like it just follows from this. Okay. Okay, good. So that's all I wanted to talk about for that. Do you remember that exercise I said? Like if you have all those sets and they were union closed, you didn't have time to do that. I don't know if it's worth talking about. Okay, maybe I'll skip it if you didn't do that one. Okay. It is kind of interesting. Maybe we just need to learn a bit more. Okay. Sets. Okay. I mean, we talk about groups. We need to know what sets are, sort of. And what we have as sets is like sort of we have naive set theory. It's like what is called before you have axioms.
Oh, okay.
Right, and then it's like a mix between that and we have sort of axioms for sets. I don't know. We're not really going to do with this one explicitly, but I might mention some as they come up. Yeah. So, for example, one axiom of a set is that 2 sets are the same if they have the same elements. Yeah.
Yeah.
So, like x equals y, if and only if every element x in x, then x in y, and if every y in y, y in x. Yeah? So that also shows, like if you have a duplicated element, like if you list it twice, it doesn't change the set because the sets are the same if it's just there, right? Okay. So then I kind of want to introduce the notion of a function, and one thing a function does is actually relaxes this definition of equals, yeah? Because saying they're equal means they're the same elements, right? But they might not have the same elements, but they might kind of be, as far as we're concerned, the same as sets. So basically we're going to show eventually that like if 2 sets have the same number of elements, it's enough. Okay. Okay. So what is a function? Yeah. So a function, basically, we might write it like this. Like you have 2 sets, x and y, right? And and you draw an arrow, and then maybe you call it f. Yeah. The function f, maybe it looks like that. Yeah.
Yep.
X to y, or like xy with f on it. Yeah. And the function has the condition that every x in x is assigned something.
Yeah. In one.
Has one output. So maybe we call this input, right?
Yeah.
Has one output y and y. Yeah? And maybe you call it f of x. Okay? And then the rule is that, like, for every x, you can only have one f of x. You can't have more than one. Okay?
Yeah.
So, like,
Well, for each
f of x only depends on this x.
Yeah.
So, like, once you input x, the output's determined. Okay? And it has to be inside y. Yeah? That makes sense? So every input has to be taken care of. And
every input has a output.
every input has an output inside of the set.
Yeah. And before it's unique to the
Yeah, like you can't have two different outputs for the same input.
Yeah.
Yeah. So this is called the domain. I guess this is called the rule. This is called the codomain. Yeah. Does that make sense? Okay. So I guess since I want to do it this way, so it's a little bit more interesting. And I had to warn you, like this is where like it's very confusing for people who are not on top of things. But I feel like you guys are ready for it.
No, exactly.
Yeah. Well, yeah. If you're playing with the slidey game thing, when you're not on top,
It's mental stimulation.
it's mentally diverting you from the thing that's mentally challenging. Okay, so that's the definition of function. Okay, so I guess I have one question for you. Maybe we have time just for like a couple of questions. I'll try to keep them relevant. So, oh yeah, I also want to mention. So my idea of a set. Okay, so it's like you have like objects, right? Like mathematical objects. So they're well-defined things, right? So that's what you need to have a thing. And a set is kind of like making. So like when you put those things in one place is when you have a set. Yeah. So like if you want to talk about like I don't know, like what were we talking about before? We're talking about geometry, right? We talk about points and stuff, right? To talk about them, they have to be sort of like mathematical objects.
Yeah.
Does that make sense? They have to be defined enough to talk about. Yeah. So what a set is, it's sort of like putting them into the same place has to be a well-defined enough notion to talk about. So it's making the togetherness a mathematical object. Does that make sense? So like a point is a mathematical object in geometry, right? A line is a mathematical object in geometry. The set of like this point and this line, right, is like the mathematical object that represents their togetherness. Those two things being together.
Yeah.
Yeah. And so, and that togetherness has to be well defined, right? So I guess the way I'm saying it is it's closer to the naive set theory than the axiomatic set theory. But thinking about it like that, it like does help you with some intuition, like why the set of all things is not a set, right?
Yeah.
It's because you can't. It's not well defined enough. It's not. Putting everything together is not well defined, right?
All things,
Yeah.
like everything.
Yeah, because it depends on it depends on whether itself is defined, right?
Yeah.
And that makes it not well defined. Because to define it depends on whether like the outcome of whether it's well defined or not. You know what I mean? So yeah, like but we won't have to worry too much because we're dealing with finite sets, right? It's very easy conceptually to put a finite number of things in one place. Though sometimes only because you can't imagine very big numbers. Because like, yeah. And then you have this side, and then when you put infinite things in one place, it naturally leads to a notion of closeness for some reason. That's another topic. All right. Okay, so we have this definition of function and some idea of sets, right? Can you give as an exercise. Okay, so can you list all the functions from 1 to 2 to 1 to 2? List all functions. We'll list all rules for that domain and that codomain, yeah?
Identity. Identity. Yeah. Identity is on
Yeah.
then for 1 it goes to 2, for 2 it goes to
Yeah.
1.
Okay, this is weird because I'm basically talking to you because you both understand this already and you're not listening.
Wait, what? I'm listening.
So I could just skip all this.
I'm listening.
Okay. Well, can you list the functions?
List the functions. Like 1 and 2.
No, it takes one. It takes an input 1 or 2, and output either 1 or 2 based on the thing.
So it's 1.
You can't have the same thing for
So one thing can't go to 2 things.
Yeah.
But both things can go to 1 thing.
Oh yeah, you can.
Yeah.
Oh yeah.
And 1. So like f of 1 could be 1, right? F of 2 could be 2. And that would be a function, right? And that's called the identity function.
It can be 1.
It could also be 1.
Yeah.
Wait, can F of 1 can F of 1 be 2?
No, because then you have one input that gives 2 outputs.
Okay, so this is one example of an f, yeah? Maybe we can have a g, right? G of 1 could equal to 1, yeah? And g of 2 could equal to 1 as well. That's a function, yeah? So maybe, is it obvious what can you compose functions? You know what composing functions is? So if you have functions from x to y and y to z, right? Yeah, the natural operation on them is to put them next to each other, yeah?
Yeah.
So then you have a composed function.
Yeah.
Yeah? Yeah, so you understand what that means? So the input of this is output here and input again, yeah? Okay, so then the question is, list all the functions, does it form a group? Does it form a group with the operation being composition?
Oh,
So now it's getting more relevant.
sure.
Do you understand what I'm saying?
So
So I'm saying list all the functions from here to here, yeah?
Mhm.
They clearly all compose with each other to give you other functions from here to here, yes?
Oh,
Does the set of those functions with the operation of composition give you a group? Does the question make sense?
Yeah.
wait, so like do the functions, the composed functions give a group, right?
Yeah, so for example, like let's call this f and this is called g, right? There's another function that takes them all to 2, yes? Or have you listed all the functions? How many functions are there?
Well,
I think there's someone good G.
So what's another function?
H1 goes to 2.
h1 goes to 2,
H2 goes to 1.
so you swap them, yeah?
Yeah, and then you have
And then
H1
let's do
goes to
k.
Go to 2.
K1 goes to 2 and K2 goes to 2.
Yeah, so are we in agreement? These are the only functions?
Yeah.
So there's 4 of them, right? So do they form a group?
So are these groups
So like is the set f, g, h, k, right?
groups?
With the operation composition, right? You know what I'm talking about?
Yeah.
So you have these 4 functions, you compose them, right?
Mm.
So groups are things with a set and operation, yeah?
Yeah.
And there's three axioms, right?
Yeah.
Should I just show you, like, is it obvious that composition of functions is associative?
Yeah.
Can we assume that if it's
Yeah,
obvious?
it is.
Yeah, okay, let's assume it's associative. Okay, so then we just have to check if there's an identity,
And
and if there's inverse for everything, right?
Yeah. like the inverse of stuff is just composed the other way around, right?
Hmm?
If you just compose everything the other way, like if you say if you compose f and g and see what happens, I guess.
Yeah. So I mean, what happens with f and g, right?
Yeah.
Well, can you actually see f? The inverse of f should be h. Can you see that?
Oh yeah. Inverse of f is h.
Well, for that to make sense, what's the identity then? Like this composed with this equals the identity, right?
Yeah.
So what's the identity in this?
F will be identity.
Yeah, f is the identity, right?
Yep.
Oh, sorry, I think I said the wrong thing. H is the inverse to itself.
Yeah.
Yeah, so f is the identity, right?
Yep.
So can you see f composed with everything does nothing to it?
Yeah.
Right? Because if you send it to 1,
If you f of anything, it will still be the same.
it'll be the same. Can you see that?
Yeah.
You see that?
Yeah.
Because f doesn't change, right? So f is the identity. And it was called the identity function here,
So
right?
that's not unique.
Yeah. Okay, so if this is the identity, so it's obvious that h is its own inverse, is it?
H is its own inverse. Yeah.
Yeah. So this h is equal to h inverse. So h composed with h is equal to f. Yeah. Okay, so that means and then obviously f is its own inverse, right? Identity is own inverse. Yeah. Yeah.
But then the other ones don't have inverses because they send the same thing.
Yeah. Yeah, so they don't have inverses because they degenerate, right?
Yeah, and then from one thing you can only get one out, whatever.
Yeah, you can't.
So you can't split it.
You don't know where one goes, right?
Yeah.
But definitely function. So these don't have inverses, so it's not a group. Yeah.
Yeah.
But so we're not. See, can you see how because we did groups first, we have more different kind of questions we ask when we learn functions. So it's a different, interesting relationship. Yeah.
Yeah.
Okay, so this doesn't form a group, right? But we do find that there is a group. Yes. We have f and h form a group.
Yeah.
Right.
Yeah.
F is identity and
F is identity and H, I guess.
H is its own
Yeah.
inverse and F is its own
Yeah, they are both.
and its associated.
Well,
Yeah.
but do they have and I guess H would be the universal inverse.
Yeah.
Yeah.
So.
It would.
Okay. No, because in a group you need a unique universal inverse, right?
Not universal.
A
unique one for each element. Like one. So
it's
universal,
yeah.
relative to h.
Okay, yeah.
It's unique relative to h. So yeah, f is its own inverse, h is its own inverse, right? Yeah, there's a lot of comments I want to make here. Just see if I can make them all in one go in sequence.
Did he say?
So can you see this is actually a group that we know? Can you know what group this is?
The switching permutations of two.
Yeah, it's the permutations of two elements, right? So, I mean, did we define it as functions? We didn't define functions then, right? So another way of saying that is it's isomorphic to that group, yeah. Because you can have a lot of different letters here, but the point is the multiplication table is the same, right?
Yeah.
This times this is equal to itself. This times this is equal to 1, and they times each other to equal h, right? And so there's another group that does that. Remember, we had z mod 2 was the remainders when you divide by 2.
Yeah.
0 and 1 mod 2.
Yeah.
Because if you add this to itself, you get itself. If you add this to itself, you get that.
Yeah.
You add them together, you get that, right? So they're isomorphic as groups. Does that make sense? Yeah. So another way of saying when sets are equal, we could have changed 1 and 2 to A and B, right? You know what I mean? It didn't really matter what the letters were or what the objects were, as long as there were two objects. Sort of the functions were kind of similar, and they did lots of similar things, right? So we're going to say two sets are equivalent, okay, or two sets are isomorphic, yeah. So let's write this down. X and Y are isomorphic, so they're equivalent. Isomorphic, yeah, in bijection. These are all kind of similar words.
Okay.
in bijection or like, yeah, I think I've said enough words. If there's a function x, fx to y, right?
Yeah.
And g from y to x, such they're inverses, right?
Yeah.
So basically, if there's an invertible function, so this is a bit of an abusive notation because one is an identity on a different set. Yeah. Yeah. So when you do sets, it'll turn out that like all that really matters is how many there are in the set. Yeah.
Wow.
So yeah, it's almost like it's a waste of the like going through all the trouble of making something really well defined is almost wasted in the set because you only just care about how many of them there are together. And so maybe that's exactly the point of the set is how many you can put in together. That's the difficulty of defining a set. Is the notion of making 6 things together well defined. You know what I mean? Whereas the things themselves, you kind of just take for granted that they're well defined. You know, this could be like a car or like a 2 or a 3, but you don't really care. You just have to. You just have to know that they're different from something else and they're together. You know what I mean? Okay. And the same with groups, right? You have 2 things. If you can find a function, so now there's a different notation. So you have a function to correspond to things, but the multiplication has to also correspond for the groups to be equal. Okay? So the functions have to be group homomorphisms. So they have to respect the operation. So for example, you need like, so like, you know, if here f times h, f composed with h is equal to h, right? And you know, f composed with f is equal to f. H composed with h is equal to f, right? And h composed with f is equal to h. And these are the only ways you can multiply these 4 things, right? Then sort of the bijection that you have must also respect this. You know, so if we have 0 and 1, and we have like a function like phi that takes 0 to f, right? And 1 to h, right? And then the inverse of that is like say this other phi takes f to 0 and h to 1, right? Yeah. Not only do they have to be a bijection, but they also have to preserve the multiplication. So for example, like phi of 0 times 1, right? Or plus 1 in the case it's a plus, right?
Yeah.
Has to equal phi of 0 composed with phi of 1, right?
Yeah.
And it does because so this is this extra condition. So like for sets to be equivalent, you just need a function that corresponds to them. Yeah?
Yeah.
But for groups to be equivalent, okay, you need the function to correspond the elements. So they have to be equivalent as sets.
Yeah.
But the multiplication has to also be preserved. Okay? Because groups you care about the multiplication. Yeah? So here you need the like 0 plus 1 has to correspond to 0. The images compose with each other, right? So here 0 plus 1 is just 1, right? So that's just phi of 1, yeah?
Yeah.
And here phi of 0 and phi of 1, well that's just f and h, right? Okay, and then phi of 1 is just h, yeah?
Oh.
Can you see that?
Yeah.
And f composed with h is just h, right? So this is satisfied. And it has to satisfy. So basically, you have to correspond the elements and the multiplication table. Does that make sense? Yeah. Yeah. So for finite sets, it's easy, right? There's one equivalence class for every different number of elements. For groups, it's obviously not as easy. So yeah. So we see like obviously there's only one element, there's only one equivalence class of sets, and there's actually only one kind of group because that one element has to be the identity, right? But obviously there's infinitely many different ways to represent that, right? That's why we care about isomorphism. We only care about the multiplication. We don't really care like what the things actually are, you know, whether they're functions or if they're just remainders. You know, we don't really care about the difference. We just care that they multiply the same way. Yeah. If you have two elements, I think there's only one way to make them into a group. Okay. So one of them has to be identity, right? And the other thing can't be the identity because it's unique, right? And then the other thing would have to have itself as the inverse, right? And the identity would obviously be inverse to itself.
Yeah.
And then they would have to multiply to the other thing, right?
Yeah.
So there's only one group up to isomorphism, even though there's many different groups, right? Just as we can represent it as functions or we can represent it as remainders. Yeah, okay. I'm gonna have to set the rest as exercises. So we have the notion of a subset. You understand what a subset is, right? So a subset is like if every element of X is an element of Y, yeah?
Oh, okay.
So when they're equal, so they're both subsets of each other, yeah? If it's a subgroup, yeah, subgroup, it has to be a subset, and the operation on the big group restricted to the small group has to make
The small group is
the smaller set of group as well. Does that make sense?
Yeah.
So basically, the inverses of the things in the smaller thing have to be all in there as well, and the identity has to be in there. Does that make sense?
Yeah.
Okay, so the quantity exercise question, I'm going to ask you sort of like find all the subgroups of the 6 elements. You know, like I'll make the bijections on 3 things. Find all the subgroups. So that's a group, right, with 6 elements. Find all the subgroups. Yeah. But yeah, we don't have time to do that. Yeah, I think it's good to do lots of examples before we do like the main theory, because then it'll be obvious. Because one of the things is the size of the subgroup should divide the size of the whole group, and that feels a bit too abstract. But if you look at the examples, it'll be clear that they all do, at least. Yeah. So maybe I'll just write that at the very end. Yeah. So this is an X. I'm gonna write it like this: H subgroup. And maybe to relax this condition, it's like if there's an injective function from X to Y, then sort of X is less than or equal to Y in the sense that, you know, like
Okay.
then there's less elements, right? Subgroup, you can also say it's like isomorphic to a subgroup as an injective function. But like, yeah, there's lots of if H subset G and the operation of G restricted to H makes H a group, yeah? And exercise. List functions from 1, 2, 3 to 1, 2, 3, yeah?
Yeah.
and then sort of keep the invertible ones. No, that's how we sort of defined S3, remember? That's S3. And then, so find all subgroups. Okay. And then I'll send you some more exercises as well. But this is one that we were meant to have done in class today. Just a bit disorganized, I'm sorry.